Thank you, Michael, and I'm delighted to be with everyone today. As Michael said, this is going to be kind of a how-to methodology talk. I'm going to go through an example of a paper that applies regression discontinuity, and we'll kind of talk about the basics, the methodology behind it, talk about issues with validity, and being able to interpret the results. All right, overview of what I'm going to cover. So a regression discontinuity design in general is part of this broader suite of quasi-experimental approaches used to get at or determine the effect of a certain intervention, whether that's a program, policy, etc. And how regression discontinuity works is it's used specifically in the instance when there's some sort of cutoff score on a variable, whereby that cutoff score determines whether or not an individual receives the treatment or is part of the comparison group. And that cutoff score in and of itself is unknown to the participants. So participants or the individuals that we're studying can't sort of manipulate themselves on one side of the cut point or the other, or in other words, into the treatment or comparison condition. So if an individual's value of this assignment or forcing variable falls to one side of the cut point, they may be assigned to a certain treatment. We'll talk about some examples of this. If they're assigned to the other side, they would be part of the comparison group. And what we're talking about on this assignment variable is a variable that spans a continuum of values whereby a certain value serves as the cut point. So it's a continuous variable that we're talking about. Now there's some similarities with another suite of methods that are often used to uncover treatment effects of programs, the difference in differences approach. The similarity is that this assignment to treatment or comparison is again determined exogenously outside the actors or the participants in the study. And there's this important notion of being able to difference out sort of these pre-treatment or starting differences that exist between individuals that are part of the treatment group or comparison group. Will work? There you go. Oh, yeah, there we go. Look at that. I can just stand out here. I'll give you a couple of examples of this technique as it's used in literature. This first one we're going to talk about today, but we're going to look at how cohort size, let's say an incoming cohort of 9th graders into high school, based on how many students there are in that cohort, there's certain cut points at which it's determined, okay, we're going to have smaller classes with the number of individuals in this cohort, or one large class. We'll talk through that in more detail. Another example, the effect of Headstart funding on child mortality. In this paper, the researchers looked at some of the early implementation of Headstart, or the early effects of Headstart funding, whereby some of the poorest counties in the country submitted applications to receive additional Headstart funding, and then based on where their application was scored, based on needs within that county, prior funding, etc., certain counties on one side of the cut point received additional Headstart funding, others didn't, and they looked at the impacts on child mortality. Another example, looking at the impact of summer remedial coursework on student achievement. Based on a student's test scores in the spring of 3rd grade, if an individual scored below a predetermined cut point, they were sent to summer school. Individuals scoring just above that cut point continued on as normal in the fall, and then you can assess the impacts of remedial coursework on student achievement. We're going to specifically look at the Angrist and Levy example, where they use a regression discontinuity design to investigate the relationship between class size and student reading achievement. Some of the literature background on this general theory is that students in smaller classes will perform better as they're receiving more individualized attention than students in larger classrooms. Now, students aren't randomly assigned in this context to a large classroom or a small classroom. That'd be your standard experimental sort of conditions whereby we want to look at the effect of small classes compared to large classes. Instead, they use an exogenous class size assignment mechanism based on Maimonides Rule. Now that some of the high holidays have just come to completion, it's fair time that we talk about a rabbinical scholar and his rule from back in the day. Yeah. So this rule states that class sizes, and we're going to use just the lowest cut point here, the smallest example, to go through this process and kind of unpack what the regression discontinuity design is. The rule states that class sizes should have just one teacher for an entire class of 40 students. But once there's the 41st student in that classroom, then another teacher should be hired, and it divided into two classes of 20 and 21 students. So if there's a cohort of 40 students, you have one large class. If the cohort size is 41 students, then you have two smaller classes. And what we can do is look at this cut point to assess the effectiveness of being in one large class versus being part of a smaller class. And as this rule follows along, it occurs, that cut point, at every 40 student increment. So at 81 students, we'll then divide into 3 classes from 2 classes, so on and so forth. And what we're going to do is we're going to use a lot of visualization today to sort of bring out the aspect of being able to look at the impact of a cohort that's a size 40 and is just one large individual class versus a cohort of 41 students of 2 small classes. So what the researchers are trying to get at here, it has nothing really to do with the cohort size itself, but it's really the effect of being in a smaller class versus a larger class, and their outcome of interest that they're going to take a look at is student reading achievement. And by the way, if you have questions that come up as we roll along today, please don't be afraid to ask. I spend plenty of time hanging out with economists, and they love to interrupt everything. So what we're going to use today to illustrate this example is data from the Angrist and Levy paper looking at the effective class size on student reading scores. Now, in front of you, we've got a plot of the entire data set. So these are all of the different classrooms that the, or all of the different school classrooms, yes, that the researchers took a look at. Along your y-axis here, you have a verbal test score. We don't really care about what the scale is at this point. Sorry, psychometricians in the room. On the x-axis, we have the size of the September enrollment cohort, so how many students are entering in a certain grade in an entire school. So everything here is aggregated at the class level. Now, if you're just taking a look at this broader picture of the relationship between cohort size and class achievement, there's nothing too much that jumps out here. Maybe as cohort size is increasing, maybe there's a slight increase in overall test scores, but that's not really what we're after. Instead, we want to drill down to the specific rule. So focusing on the application of Maimonides Rule, that demonstrates the difference between individuals enrolling in a larger class or a smaller class. So up to 40 students per class, the entire left-hand side of this dividing line, all of these individual classrooms, the data plotted for the individual classrooms, represent large classes. Okay? So for example, your cohort of size 36, within that school there would just be one class of 36 students. Up to this cut point, once the 41st student is enrolled in a school as of September, entering the school year, then classes are divided into 2 smaller 20, 21, 22 person classes. So for all of the classes on the right-hand side of this cut point, all of the classrooms are smaller in terms of the number of students in the class. And that marker at 41 students, that's where things first get divided. So I got that red line in there indicating the cut point, or the dividing line, between students in the smaller versus larger class condition. So at first glance, it doesn't appear that there's too much of a relationship. If we were just kind of focused on the left-hand side of the dividing point for a second, and then conversely looking over to the right-hand side, we don't see much in terms of a pattern here. But we have to keep in mind that we're trying to get at the effect of intended class size. Well, we can break this down, simplify it a little bit so that the pattern taking place becomes a little bit more clear. And we're going to start by looking just around that cut point. Okay, so we're going to look at specifically all the classrooms where there was a cohort of 40 students, so one large class, the comparison condition, versus all of the classrooms where there was an enrollment cohort of 41 students, so two smaller classrooms on either side. Now, if we just take a look at these two sets of cohorts of students around the cut point, we can see, at least from the picture, that it appears test scores are higher for individuals in the cohort of 41, or the smaller classroom, versus those in the larger classroom, single classroom of 40 students. To help better visualize this, we can condense it down to the means of each of those groups. So all I've done is go from all of the data points to, within each enrollment size, the mean of each group. So we can easily visualize, looking at the mean difference of the cohort of 41 students compared to the mean of the cohort of 40 students, and again, that's comparing small classes versus large classes, we can calculate a first difference. Okay? Our initial sort of naive estimate of the impact of being in a smaller classroom versus a larger classroom. So we might come up with that difference of 5.75 points, walk along our merry way and say, hey, small classes are better. But we know it's not that simple, and it appears already from this simplistic picture we're ignoring a lot of data points. We're going to get into some of the assumptions of what this estimate is going to be able to allow us to say, not be able to allow us to say in a few moments, but I want to keep working through the mechanics here for a second. Now, just as is the case with if you're looking at a kind of simple difference in differences approach, we haven't taken into account any sort of pre-existing trends. In other words, there's other data trending out here which may influence the trend of test scores as cohorts get larger. And similarly on this side, other data out in here that may influence the trend of test scores, again, as cohort size gets larger. So to determine these existing trends, we could start by looking further back at cohorts of size 38 and a cohort of size 39. Now these individual cohorts, again, I've got the means of all the classrooms. These represent large classes. One class, 38, 39 students, up to 40 students before the class sizes are divided into two smaller classes. Now, there may be an underlying trend here that's occurring between a cohort difference of 38 and 39 students. We can take a look at what that trend is and then subtract it off of the difference in the trend from 40 to 41 students. Notice that we're just talking about an increase or a difference of one student between these groups that we're comparing. Okay? They're near each other, but we're still talking about a one student difference. In comparing 38 versus 39 students in a cohort, we're looking at two large classes. In comparing the difference of one student from the cohort of 40 to 41 students, we're comparing the difference between a small class and a large class. So there's still a one student difference between these cohorts. And if we think about some of the other background characteristics of these students, cohorts that have subclass size 38 and 39 on average should roughly be similar to one another, as should cohorts of size 40 and 41. The only notable difference is whether or not there is one class versus two classes here. So we can calculate what the difference is between this comparison condition of one student difference versus this treatment condition of a one student difference. So we find that second difference, take it off, and come up with our kind of broader difference in differences estimate, taking out sort of what trend existed on the left side here from the treatment estimate we find on the right side. So we now have an adjusted difference of 4.73 points. Okay, we've done a little bit of a better job here. We've sort of accounted for underlying trends that might exist in the data. We've taken that off of our estimate of the treatment effect. So we've got a cleaner, less biased estimate than the first difference estimate. So we might run off and say, oh great, smaller classes are better, but that's still not the end of the story. If we only look at the closest, in this case from 38 to 39 students, the closest difference in nearby cohorts, we could be throwing out information. We can always expand our bandwidth or our window in which we're looking at trying to identify the treatment effect to cohorts of progressively smaller and smaller sizes. Now, if we're truly trying to get at what sort of trend exists between increasing cohort size and test scores for all the large classroom cases, we could actually plot a trend across a greater set of data points. Now, accounting for this sort of broader trend that's occurring just within the comparison condition of cohorts from 36 up to 40 students will give us a new estimate of the treatment effect. We can extend that trend line all the way to our treatment condition and find this adjusted difference of 5.12 points. In the previous example, I was just taking into account this difference of one student in the nearest set of cohorts. Now I'm sort of expanding my window to get a better picture of the underlying trend between cohort size and test score. And just to be clear, we estimate that adjusted difference using all of the data points. What I displayed for you on the previous slide is just within each cohort, everything condensed down to the individual mean so that you can pick out the trend a little more clear. If we just use the aggregated means, we'd get the same result, but we'd have a lot more noise because we have fewer observations as well. Now, to help us think of this in the regression context, and just for a moment, this is going to be important for estimation later on, I've just recentered this variable down here. So 0 represents the cut point, and then to the left side of that cut point, one fewer student than the cut point versus 1, 2, 3, 4, 5 more students from the cut point as well. That'll be important for estimation. And again, to be clear that at the cut point itself, again, I'm just displaying the mean, but there are classes, there are multiple classes with cohort size 41. And you can see that there's about twice as many data points along there, and that kind of makes sense because there should be twice as many classes if assignment to treatment occurred. So now what I'm going to do, we've accounted for what trend is going on within the comparison condition. We also want to take into account what underlying trend there is between cohort size and test score for the treatment condition. So we've already made an assumption about the trend before the cut point, but there's certainly one after it as well that we need to be concerned about. If test scores are just increasing as cohort size increases, we want to take that out so we can zero in on the impact of the treatment effect of being in a smaller classroom. So if we were to plot the trends on either side, the trend of the comparison classrooms, the trend of the treatment classrooms, we'll sort of be accounting for these pre-cut point trends, post-cut point trends, and then the discontinuity, the difference at the cut point, represents the treatment effect. Remember, all the classes are lying underneath the cohort averages. I'm just showing you the individual condensed averages, and we can look at this from a centered perspective as well, where 0 is the cut point, and then we have progressively smaller, progressively larger cohorts as well. So before going forward, just to review, I'm trying to focus in here on the adjusted difference between adjusted test score difference between individuals enrolled in smaller classes as a result of having a large enough cohort size versus larger classes. And in order to get a cleaner estimate of that impact, I need to account for the trends that are underlying the relationship between cohort size and test score. Now, what I've done is I've made previously an assumption just using data on the left-hand side and data on the right-hand side to get at the two trends. There may be an underlying trend that exists across the entire data set that we want to take into account. In other words, the trend that exists between reading scores and cohort size. So instead of trying to plot a differential trend for the comparison classrooms and a differential trend for the treatment classrooms, I could look at the picture as a whole. And if we use this same trend on either side of the cut point, let the cut point serve as the jump or the difference between the two groups, we have ourselves the regression discontinuity treatment effect. Now, what does that look like in terms of a regression equation? Beta naught represents the intercept, so it is the average test score for the comparison group at the discontinuity. Beta 1 is the treatment effect, or the difference in test scores between small classes on the right-hand side and large classes on the left-hand side. And beta 2 is that underlying trend that accounts for the relationship between cohort size and test scores. So the mean reading score, beta 1 is the mean difference in the reading score between small and large classes, or the average treatment effect. Beta 2 is the slope between the forcing variable and test scores. It's a control for any sort of underlying test score trend that exists between cohort size and test scores. Any questions before I move on with this discussion? That's giving you kind of a graphical mechanics behind what's going on with regression discontinuity. Now, there's several things that we could take into account when we are actually trying to model this. Okay? We first made an assumption that fits pretty well in this instance, that there's some sort of continuous linear relationship between cohort size and reading scores. And this is reflected by just estimating a single continuous linear trend, or the secular trend, between cohort size and test scores. Now, we could modify this approach to better fit the data. The first is that we could fit an overall trend that takes kind of the underlying functional form. Maybe it's not a linear model. Maybe it's a polynomial model. Maybe it's a non-parametric equation. All of the regression principles that you've learned come into play here in terms of how you would model that underlying relationship. We could fit two different trends taking any functional form. Similar to what I started out with, we could fit a pre-treatment trend, we could fit a post-treatment trend, and then that jump, that difference at the discontinuity, will represent the average treatment effect. Again, any of these considerations go back to regression analysis principles. And just the one thing to sort of bring home to highlight, we want to account for those underlying trends, otherwise we may over or underestimate the difference between the two groups. For example, if there is a upward trend for the comparison group and a downward trend for the treatment group, the averages may be a difference this big, but if I'm not accounting the direction that they're trending, I'm going to overestimate the actual treatment effect of having a smaller class size. Now, I've also just proposed the sort of simplest model for uncovering the treatment effect using a regression discontinuity design. As with any regression analysis, we may consider accounting for covariates for all of the individuals in the data set. So other background characteristics that might influence why a student is attending a school with a cohort of a certain size and their reading test scores. We could account for school characteristics in here, turn this into a multi-level model. We could look at how this changes over time or across grade levels, anything else, and how you would build up your regression analysis model would still come into play here. Now, there's some important implications about, I talked about looking at this sort of range of cohorts on either side of the cut point to get at the underlying trends. But I can choose how wide that is. I might look out in either direction. 10 student size cohorts in either direction. So for example, from 31 to 40, and then 41 to 50. So we can test various bandwidths for fit in the model. But in any time the bandwidth is changed, sort of the width in which I look at this impact, it's going to have estimation implications. We increase the bandwidth. We're going to have more data points part of the analysis, less standard error. But that's also going to have validity implications as well. And we'll talk about those considerations in just a second here.
I may be stating the obvious here, but if you went to a 10, for example, we would have potentially a class of 30 and a class of 30.
If we go 10 in either direction, yeah, it's possible, right? So if the cut point is at 40 or at 41, we would divide the classes into 20 and 21. But if we go up to if we go up to 50 students in the cohort, it's possible that the cohort's divided into a class of 20 and 30, and we'd be comparing that to 30 students. So you kind of lose some of your treatment with that. The assumption is the further you're going out, things are being divided equally. So you'd be comparing two classes of 25 students versus a class of 30. Not really much in terms of a smaller class size versus a larger class size in that point, but specifically with this rule, yeah, the actual treatment condition in and of itself may look a lot different, certainly further and further we go. Okay. Let's talk about internal validity. What can these estimates tell us? Well, the key assumption here, the key underlying assumption for us to be able to say, hey, our estimate of the discontinuity effect is the average treatment effect of the program policy intervention that I'm taking a look at, is that the observations closest to one another on either side of the cut point should be equal in expectation on a set of pretreatment covariates. In other words, in the Angrist and Levy example, there should be little difference on average between students in cohorts of sizes 36 to 40 compared to 41 to 45. That becomes a little more clear when we look at the cut point itself. In terms of a school that has an incoming cohort of 5th graders, let's say, that has 40 students in it, versus a school that has an incoming cohort of 4th graders that has 41 students in it, we would expect, if we take an average across all the different schools with a cohort size 40, cohort size 41, that the achievement of the classes should be roughly the same. Prior achievement, that is, the funding, the school resources, all of these background or pretreatment covariates should be equal roughly on average to one another. The only difference between that cohort of size 40 and the cohort of size 41 is that the cohort of size 41 gets the intervention of being able to have the students in a smaller class versus a larger class. Okay? The difference between the two groups is one large class versus two smaller classes. There's implications of the bandwidth choice, certainly on internal validity. The smaller bandwidth that we take a look at, those cohorts of similar size should be more similar to one another than if we extend the bandwidth out. Dr. Jensen's sort of gotten at an example of that already. A school that has incoming cohorts of size 30 is probably going to start to look a lot different from a school that has an incoming cohort size of 50. That put aside class size for just a second. That says something about kind of the population of the area that it's drawing from. It may say something about resource differences of the schools, etc. But in terms of a difference of 37, 38, 39, 40 students in a cohort versus 41, 42, 43, there shouldn't be, on average, much difference between these schools. The only difference being the treatment itself and how that gets assigned. Now, there's also an important threat to validity here, and that's manipulation of the treatment status around the cut point. So, for example, if I'm a headmaster of a school that has 40 students in the incoming cohort, now the rule says I should have one class of 40 students. but maybe I got a little extra money coming in this year from a donation, so I'm going to hire another teacher anyway. So rather than that cohort of 40 students being assigned to one large class, those students aren't getting the treatment as well. Or it could work in reverse as well. I'm penny pincher headmaster, and even though I have 41 students in my incoming cohort, I'm only going to assign those kids to one classroom, one teacher of 41 students. So the only way that our underlying estimates are true estimates of the treatment effect is if there's this sharp discontinuity. Everybody that is below the cut point does not receive the treatment in this case. Everyone that is above the cut point does receive the treatment. And we can conduct a test where we take a look at the distribution or the density of receiving the treatment or not receiving the treatment around the cut point. That should be a smooth process. I'm not going to go into details about the McCrary test, but if there is a discontinuity, that suggests that some observations are able to manipulate their assignment to treatment condition. I'm not talking about discontinuity here in terms of the treatment effect of test scores. I'm talking about a discontinuity. It should be a smooth assignment. Everybody that is below the cut point, we should see that none of them are assigned to treatment. Everybody that is above the cut point should all be assigned to treatment. There shouldn't be any sort of convergence. So you may have the question, well, in practice, things don't go perfectly. People cheat. We know that that happens. So what happens if manipulation occurs? Or if individuals are not perfectly assigned to a treatment or comparison condition at the cut point? What do we do in this case? An example of the latter, individuals not being perfectly assigned, you may have, I think the summer school case is a great example. A child scored just below the test score cut point. They were assigned to attend summer school, but the parents begged to the principal, please don't send my child to summer school, I don't want them to go, and then they never end up going to summer school. Okay, so that could be an example of non-perfect assignment. Well, we turn to fuzzy regression discontinuity as opposed to sharp regression discontinuity design, and that involves an instrumental variables approach. I'm not going to go into the details of this, but now that cut point, the forcing variable that helps determine assignment to the treatment condition, is used as an instrumental variable to predict the likelihood of receiving a treatment. That's the first stage of the instrumental variable. And then we use those predicted likelihoods of receiving treatment as an instrument to help us get at the effect of the treatment on the outcome. So we're sort of using it as a first stage, second stage approach in that the regression discontinuity itself is going to be helpful for determining who's getting treatment, who's not. It's not perfectly assigned. And then we use those estimates as an instrument to get at the effect of what the treatment is on the outcome. As you have internal validity concerns, you've got external validity concerns as well. Remember the key underlying assumption of the regression discontinuity design, it all hinges on assignment to treatment around a certain cut point. So if we're coming up with an average treatment effect around that cut point, it's only going to be generalizable to observations within the bandwidth we have chosen. So the smaller bandwidth that we choose, we're only going to be able to generalize to cohorts of that smaller size. Maybe cohorts of size 38, 39, 40, 41, 42, 43. The wider that we make the bandwidth we're investigating, our external validity increases. So there's a really important trade-off here in terms of the bandwidth choice. The closer we're looking at the cut point itself, we have greater internal validity, but we're going to have fewer observations, larger standard errors, less external validity. As we move out, it becomes less likely that we can trust our estimates of the treatment effect, but we can say that it's an effect for more people. Okay? So there's kind of this parry back and forth, this trade-off that occurs in focusing on a smaller bandwidth versus larger bandwidth. General rule of advice, general rule of thumb, start with a smaller bandwidth so you can ensure that you're actually uncovering a treatment effect if it's there, and then if you detect one, slowly work your way out to be able to make it more generalizable if possible, but recognize the trade-offs that exist in each of these circumstances. questions? I'm like blowing through the time here.
So in terms of the larger bandwidth with this example, you would think then would there be another cut point when you hit like the 80, 81?
Yeah. So this rule follows at every 40 student increment. So I'm just giving the simplistic example of looking around that first cut point of 40, but there's going to be another one at 80. Cohort of size 78 is going to be divided into two 39-student large classrooms. Same thing with 79, 80, two classrooms of 40, and then when you hit 81, divided into three classrooms of 27 students. Relatively speaking, around the cut point, being in a class of 27, 28, 29 students is a small class as compared to a class of 38, 39, 40 students. Right? Now, if there is some sort of decreasing treatment effect that's occurring as class sizes get larger, then we would expect to see the largest average treatment effect at the lowest cut point, and then it get progressively smaller because the actual sizes of the class are changing or are becoming closer and closer to one another. They're still small compared to large, but relatively speaking, the small classes are more similar in size to the larger classes.
So still on the topic of bandwidth, if the cut score or the cut point, say in the project that we're working on, is less on this issue of an intervention based on size, but is based on a student characteristic of academic preparation.
Mm-hmm.
So if we use, like we do with the APP program, if the cut score is college readiness,
mm-hmm.
just above and below the cut score, those students are going to be the most similar academically. As the bandwidth increases, you're going to have more and more higher performing and lower performing students. So in that case, I would expect the treatment size would actually increase as the bandwidth gets bigger.
Well, but you're plotting trends coming underneath it. So let's take, for example, this example of college readiness on degree completion. Okay? Or first year GPA, whatever you want to make is your outcome. And let's say, for example, we're assigning students, if the student received an 18 or a 20, okay, we use 20, I'm going to stick with 20. The student scored a 20 on their ACT math, they're considered college ready. So students that scored a 19, 18, 17 would be classified as not college ready. Those scoring a 20 and above would be classified as college ready. If it's determined you're not college ready, you have to take a remedial course. Okay? So you score 18, 19, you have to take a remedial course. 20, 21, don't have to take a remedial course. Okay? The underlying assumption is that if I score a 19 on my ACT math and you score a 20 on your ACT math, there shouldn't be much difference in terms of our math ability. Okay? You've been deemed college ready. I'm not college ready. Therefore, I have to take a remedial class. You don't. We can measure the difference between all the students who don't have to take remedial classes, scored 2021, versus those that do, scored 18, 19. What's going to happen the further that you extend out the bandwidth is we predict that there's increasing trends on either side. So as ACT scores increase, we predict that GPA is going to go up, but that's going to happen from this point as well. So they're going to converge in the middle, and we're going to get our estimate of the treatment effect. Extending it out in either direction shouldn't change the overall treatment effect because you're still going to get this convergence that results in a similar discontinuity. Yep. Now that's saying if it's a linear underlying trend, it might not be a linear underlying trend, and tail off at some point, but that all deals with model fit and whatnot. And in that case, for example, I think it's a little more clear than using our rabbinical scholars rule here, is if you now start comparing kids who scored a 14 on the ACT to somebody who scored a 29 on the math portion of the ACT, there's a huge, qualitative and quantitative difference between these students before entering college.
External trend.
Well, it's an Right. From an external perspective, but also from the internal perspective, it becomes less and less likely that the difference you're observing between those students collectively is truly a result of the treatment, and it could be as a result of, that's why you would have to control for other background covariates as well. John, for the historical treatment of regression discontinuity?
Well, I'm glad you chose Moses Maimonides rather than Solomon, because you would have had to split the children down the middle.
Oh, yeah. Yep. Wait on. I can always count on a good anecdote, as well as hearing it afterwards about putting our great Dr. Thielen to sleep.
But by the way,
okay. Now, go ahead. Yes.
That issue comes up on like classroom construction, like increasing returns to margin or decreasing returns, like like on enrollment plan. Like, do you admit that extra law student and then have to build a complete new auditorium, which they're doing across the street right now?
Sure. Yeah. No walls to keep people separated there right now. Yeah. No, literally, there's no walls left in the law school. That's okay. So in the remainder of our time here, okay. Now, I mean, you don't have to be too concerned about all of the different text here or the different commands. I'm using stata. What I'm going to do is using the same example. In fact, I could pull up a second example, time permitting, after this, where we're going to take a look at the actual impacts from the Angrist and Levy paper, sort of how you would work through regression discontinuity, what I would do, things that I'd take a look at, etc. And sort of where I got all of this information from. Okay? So start, of course, by taking a look at the overall picture of the relationship between cohort size and test score. Knowing the rule, right? Now the application of the rule, yes, it's supposed to be determined at the individual school level, but it is a rule that's kind of outside the purview of the school. They're just supposed to follow it. We can focus in on the scatter plot around the cut point. Make this bigger as well. This is going to look a lot like what you've already seen in the handout here, but here's actually doing it. Okay. Since there's a cut point at 41, I need to define a variable in my data set that indicates just that. So if I were to take a look at descriptive statistics, all of the classrooms from size 41 to 46, there's 133 of them that are now classified as small classrooms, 47 classrooms that are large classrooms, size 36 to 40. So once I know where the cut point is, be able to create that. I've already taken a look at the frequencies. I'm going to center this. And then I can start with the descriptive analysis. So the first thing that I'm going to do is take a look at mean differences between the treatment and comparison groups. So these are the average test scores. Remember, I condensed it down to just 2 individual data points for all the small classes, all the large classes. I was just looking specifically at 40 and 41. So here's kind of the descriptive mean differences between all the small classes versus the large classes. Look at this, it's about 4.8 or so points. We can, of course, conduct a t-test, or as I'm going to do, put it into a basic bivariate regression analysis to get at the treatment effect. And there's about a 4.7 point difference between the smallest classes and the largest classes. you see that treatment effect is statistically significant at the 1% level. So all I've done is the descriptive part of the work, looking at what is the average test score difference between smaller classes and the larger classes. Next thing I want to do is to take into account the underlying trend. So adding in a control for the forcing variable itself. We see that the estimate of the treatment effect decreases to about 3.8 points. And we'll also note that it's no longer statistically significant. Okay? So what I showed you in the initial plots was just the amount of the difference. We didn't talk anything about statistical significance. If we didn't take into account this underlying trend, we might think that small class size has a statistically significant effect. When we take into account the underlying trend that exists between small and large classes, we find that there is no impact of attending a smaller class. Now, in their paper, there's a whole host of additional variables that they controlled for, accounted for, tried to fit it in different ways. But the takeaway information here is that this intent to treat impact is no longer statistically significant. Now, what were to happen if we were to extend the bandwidth? Okay, so I didn't find a treatment effect within 5 students. We could try expanding it out and see what happens to the treatment effect. So I'm going to create a new treatment variable. And rerun the analysis with that new treatment variable. Right? Find an even smaller impact. Now I'm taking into account more classrooms, so the overall standard error should go down, but we still find that it's not statistically significant. Now I don't have the McCrary's test in here. It's a little long and cumbersome in Stata, but also in the implementation of this, there was almost universal perfect compliance to the cut score. So, as if it's needed here. Questions about kind of the process that you would go through, or any more about why to adjust for these underlying trends? The basics of it aren't super complicated. There's the complication in the design itself, in understanding where the cut point takes place, being able to model the underlying trend that takes place. But you can see, sure, I could make a fancier regression analysis in terms of fitting something that's nonlinear. I can make it fancier by adding other control variables that I might have in my data set. But outside of that, it's just an OLS regression analysis. There's nothing fancy beyond that. The fanciness comes in defining the treatment and comparison conditions at the outset.
I'm feeling all bummed that it didn't have an impact.
Well,
couldn't you have used an example that, where the kids win in the end?
Well, I tend to like examples where kids win in the end as well. But the important takeaway here is that you may be, if you don't account for those underlying trends, you may be tricked into thinking there's an impact. And also, they do find some impacts in the paper. I'm just looking within one of the bandwidths. When you look across all the bandwidths of size 5 around each of the cut points of various cohort sizes.
Okay. Well, thank you, Joe, for this presentation.
Yeah, sure.